The alternator, or AC generator as it's sometimes referred to, is responsible for recharging the start battery and supplying the energy needed for the vehicle's electrical system once the engine's running. The alternator forms the core of the charging system. In modern vehicles, it's a complex computer-controlled device that demands specialist tooling and training for service and repair. The conventional charging system as we know it relies on the principles of using electromagnetic induction to create current flow. The current produced by this method must be conditioned and controlled for use within the vehicle's electrical system and recharging the starting battery. Mechanical energy from the engine's crankshaft is used to drive the alternator's rotor via a belt, tensioner and pulley system. The pulley attached to the alternator is geared to rotate at speeds of up to 3 times greater than the crankshaft on a production engine. Traditionally, an alternator pulley is fixed to the rotor shaft using a taper, woodruff key or a shoulder mount. Modern alternators may even use a one-way clutch or a decoupler pulley. These alternator drive systems help improve the performance and fuel efficiency of their parent engines. They allow the alternator's rotor to coast when the engine is decelerating from high revs, conserving the engine torque that is traditionally used when slowing the rotor's momentum. The rotor is basically a controlled field electromagnet that spins in relation to crankshaft speed. The rotating electromagnetic flux produced by this field envelops the fixed stator windings positioned around the rotor. The movement of the magnetic field excites the electrons within the copper stator windings, causing them to flow within the circuit. The electron flow or current must now be conditioned and controlled or regulated and rectified before it can be of any use to the DC systems within the vehicle. The demand for electrical power within the vehicle has been met by OEMs. Their high-performance alternators use a rotor with a greater mass. An overrunning pulley or decoupling device is installed to reduce the effect of the rotor's mass on the engine. It interrupts drive from the rotor to the belt as soon as the speed of the rotor exceeds that of the pulley. The rotor shaft can therefore turn faster than the belt pulley. It also acts as a damper, compensating for firing pulses or any other cyclic irregularities. The decoupler pulley is simply an alternator pulley with a one-way clutch mechanism incorporated within. The pulley will rotate freely in one direction and lock when turned in the other. The locking effect is achieved using pinch rollers, or more commonly known as a sprag clutch. The rotor is the moving part of the alternator and provides the magnetic field needed for energy generation. The rotor shaft holds the electromagnetic coil, pole pieces, cooling fan and slip rings, and is supported by roller bearings at each end. Voltage supplied by the ignition circuit flows to each terminal of the electromagnetic coil via a set of brushes and slip rings. The pole pieces are constructed of a soft iron and are shaped so that when they are assembled to the rotor, they cover the electromagnetic coil. These interlaced poles take on the polarity of the electromagnet, concentrating the flux to the pole fingers. When the ignition circuit is completed, an alternating magnetic field is formed between the fingers. The stator has 3 separate windings of insulated copper, wrapped around an iron frame and arranged in multiple coils. The number of coils will be equal in number to the amount of field poles on the rotor. The alternating coil circuits are overlapped and positioned evenly around the stator. The ends of the coil groups are joined to form what is known as either a delta or star connection. When the powered rotor turns inside the stator, the magnetic flux from the pole pieces cuts across the stator windings. As a north-south pole crosses a coil, current is induced in that coil, beginning the process of magnetic induction. As the rotor turns, the magnetic field influences the current flow in the stator coil in one direction until the pole reaches the peak of its arc. This is the limit or peak current produced by that coil. When the peak flux of the north-south field passes the coil, the level of current descends to zero. The stator coil is now influenced by the next pair of pole pieces, although these are arranged in a south-north configuration. The current flow increases again, but in the opposite direction. Because the magnetic flux is reversed, so too will the influence on current flow within the stator coil. This process will continue inducing an alternating current until either the rotor stops turning or the ignition supply to the rotor is removed. The phases or windings are overlapped in such a way that current is induced in a controlled order. Each phase winding is configured with 120-degree separations. As the rotor's multiple field poles influence each phase winding, current is induced in each phase in order, with this same degree of separation. The faster the rotation of the field magnet, the greater the amplitude and frequency of the AC current induced into the windings. A rectifier is attached to the stator windings to convert AC current to DC current. A rectifier is simply a device containing a diode bank and heatsink that blocks a portion of the current cycle. When placed in series with the phase winding, a positively biased diode will block the negative part of the current wave, so we are only left with the positive. On a single phase winding, this would result in a fluctuating direct current supply. This is not desirable. If we attach this supply to a bulb, it would tend to pulse on and off. By overlapping all phases with this same design, we can see the pulsing current is smoothed out with only minor fluctuations. By using only positive bias diodes, we have achieved half-wave rectification. Although popular in marine and power equipment, this is not ideal in automotive applications. The ideal method of conversion from AC to DC is through full wave rectification. Using this type of method, the negative portion of the sine wave is not wasted, it is effectively flipped to a positive. We can achieve this by adding a set of negatively biased diodes to the circuit, so we now have a total of 6 diodes in the rectifier assembly. Keep an eye out for more training in this series on regulator rectifiers. The alternator now has a steady supply of DC voltage for the vehicle's electrical system, although it's still in analogue form. The rectifier has converted the alternating current to direct current effectively, but when seen with a scope, it's not a clean, stable voltage. The modern ECM and complex electronic systems on today's vehicles prefer a much more stable voltage supply. The vehicle's battery acts as a stabiliser in the same way a capacitor does. A fluctuating current goes into the positive and is balanced through the battery cells, producing a clean DC voltage at the negative post. Keep in mind, a vehicle's electrical system has an operational range of between 12 and 14 volts, so our alternator needs to be able to limit its output to keep within this range. The voltage regulator is designed for this task. The regulator controls the peak current output by controlling the size of the rotor's magnetic field. The regulator senses the voltage from the alternator's B positive terminal and controls the field supply current based on this voltage level. If there is a large draw on the electrical system, the regulator will feed more current to the rotor's magnetic field, thereby increasing the amount of current induced in the stator. When the load is removed, the voltage at the B positive terminal will momentarily rise. The regulator will sense this and reduce the size of the rotating magnetic field by limiting current flow to the slip rings. The voltage regulator constantly alters the output of the windings based on rotor speed and electrical load. It's these basic principles of magnetic induction and current control that will help you understand hybrid and electric vehicle drivelines. You owe it to yourself to learn as much as you can about this emerging technology. Thanks for watching.